Hi friends, this is Alampale Akhil. As my roll number follows on the screen, today my subject is study of turboshaft engine core noise. About a small introduction, that is a predict for a low frequency core engine noise was derived from an evaluation of an availability data as a part of a phase 4 of core engine noise program. The basic reference prediction was modified to take into the account the three huge engines types are turbofan, turboshaft and turbojet. The correlation that was based primarily on the low frequency data from the engines at the low power settings. The engine data available at the time was many cases significantly significantly influenced by the jet noise at the high power settings. Since the writing of the report, additional engine data have become available to enter into the correlation. And NASA GT8D 109 Refine engine. Low frequency core noise from a GT8D 109 Refine engine has been evaluated by the comparing this data to the core noise prediction. Low frequency core Low frequency core noise is in a percentage for this engine over a range of low power settings. Figure 2.1 shows that spectral shapes fall between the bordermost consecutive spectral envelope. Volume 3 figure 3.32 and the more narrow T64 spectrum was found to be a good approximately component combustion noise. Both those spectra are peaked at the 400 Hz. However, peak can be 1/3 octave band higher or lower. The refined data peaks between the 400 and 500 inches. The data indicates that there is a variation in the spectra shape with an angle. The refined spectra fall between the two suggested by the prediction methods. However, we can able to observe a graph on the screen where a comparison of a prediction and measure the spectral shape of a low frequency of core noise and Garrett turboshaft engine. The low frequency core noise from the turboshaft engine relatively easy to evaluate because fan noise does not exist. Plus, the jet noise is quite low. A turboshaft engine in the 840 shaft horsepower class was tested by the Garrett Air Research Company. Various suppression devices were employed and their effect measured with a Fairfield microphone located every 15 degrees on a 100 feet arc. The configuration evaluated for the core noise had a suppressed inlet and untreated exhaust duct 9.3 inches long. The overall power levels were determined from the turboshaft engine. Power level spectra, the prediction spectra envelope level and the peak frequency were fitted to power level spectra as figure 2.4. The overall level was determined as a peak level of the spectra plus 9.9 decibel, where the 9.9 decibel is the difference between the prediction spectral envelopes, peak level and overall level for the spectral shape. The overall power level determined by the method are plotted against the engine prediction parameters in figure 2.6. The data can be seen to follow the same general trends as the turboshaft engine prediction line. You can able to observe a graph that is spectral shape comparison of a turboshaft data. The third octave and level decibels, and where the line is known as core noise prediction and ground effect is known as null and turbo machinery noise. And NASA TF engine testing. NASA TF34 engine testing. The low frequency suppression cannot be seen at the higher power settings, indicating jet noise domination of the spectrum. Those observations were verified by plotting the derivatives for the affected frequencies. Core noise were present in the Fairfield spectrum. This equation has been addressed above. The valleys and peaks in the spectra could be attributed enter to ground reflections. There, the free field spectrum defined by the simple forming of a smooth line. The spectral level. The spectrum level. There are two methods that can be used to evaluate the relative effects of those other noise sources. The effect of the fan noise can be evaluated by comparing the spectral data from unsuppressed fan to a full suppressed fan configuration at the angle where core noise is expected to peak, namely 120 from the engine inlet. When the levels of the two spectrum convert, it can be reasonable assured that the fan has little or no effect on the spectrum. The presence of jet noise can be determined by examining the source pressure levels for the inducing the one-third octave frequencies bands and plotting them against the core exhausted velocities over the operating range of engine. When the slope of the plot indicates an exhausted velocity to the sixth power or higher relationship, it can be assumed that jet noise is dominating the spectrum. However, when the slope of the data indicates an exhausted velocity to the fourth power dependence, it can be asserted that some other source dominates, hence the one-third octave band levels, which could not be identified as either fan noise or jet noise, and which followed a core exhaust velocity to the fourth power are indicative of core noise, where spectral shape at higher power settings. At the lower power settings, the core noise prediction spectrum fits the measured engine at data of sixth one-third octave bands. When the engine pitch is increased to the 95Z fan speed of the slope of the jet noise spectrum approaches the slope of the core noise spectrum. The core noise spectrum still maintains a good fit 5 1/3 of octave bands. There is no indication that the core noise spectral shape differs appreciably from the prediction of the spectrum over the engine operating range. You can able to observe that a graph between engine A including engine program at 70% of fan. Thank you.